Electrons, protons, and neutrons, the invisible architects of our universe. These tiny subatomic particles are the building blocks of matter, the very fabric of our reality. But in the quantum realm, they are much more than just particles. They exhibit a curious duality, behaving both as particles and as waves, a concept that challenges our everyday perception of the world. Electrons, the lightest of these subatomic particles, are the dynamic dancers of the atomic world. They whirl around the atomic nuclei, creating a cloud-like formation. This electron cloud is not a physical entity, but a probability distribution, a space where the electron is likely to be found. This is an example of a quantum phenomenon known as wave-particle duality, where particles can behave as both particles and waves. Next, we have protons and neutrons, which reside in the nucleus of an atom. Protons carry a positive charge, and neutrons are neutrally charged. Together they make up the atomic nucleus, the heart of an atom. But much like electrons, protons and neutrons are not just particles. They too exhibit wave-like behavior, a testament to their quantum nature. This wave-particle duality is a fundamental aspect of quantum mechanics. It tells us that the nature of these particles is not set in stone. Instead, their behavior depends on how we observe them. This is one of the many ways in which the quantum world defies our intuition. Furthermore, these subatomic particles are not isolated entities. They are continually interacting with one another, exchanging energy and information. This interaction shapes the structure of atoms, the formation of molecules, and ultimately the macroscopic world that we perceive. These invisible architects, electrons, protons, and neutrons, are the foundation of our quantum universe. Their behavior, dictated by the laws of quantum mechanics, gives rise to the complex and diverse world that we live in. Protons and neutrons, not just particles but also exhibiting wave-like behaviors, form the fundamental bricks of our quantum universe. Superposition and entanglement challenge our common understanding, transporting us to a frontier where reality becomes extraordinary. Imagine for a moment a quantum particle in a state of superposition. This is not a particle in one place or another, but rather in all possible places at once. It's like the keys you lost, existing both in your pocket and on the kitchen table simultaneously, only deciding where to be when you actually look for them. This seemingly fantastical concept is not a quirk of interpretation, but a fundamental feature of the quantum world. It's as if particles are humming all the notes of a symphony at once, only hitting a single note when we listen in. This is superposition, the ability of quantum particles to exist in multiple states simultaneously. But what happens when two particles become entangled? This is where the plot thickens. Entangled particles are like cosmic twins, mirroring each other's states instantaneously, no matter how far apart they are. If one particle is spinning upward, its entangled partner will spin downward, even if it's light years away. This instantaneous connection, defying the speed of light, baffled even Einstein, who referred to it as spooky action at a distance. Yet this is not magic, but the strange and beautiful reality of the quantum realm. It's as if two entangled particles are dancing a perfectly synchronized ballet across the vastness of space, instantly responding to each other's movements. This is entanglement, a deep and mysterious link that binds particles together across the cosmos. These concepts, superposition and entanglement, are not just theoretical curiosities. They are the driving forces behind technologies that are shaping our future, from quantum computers to quantum teleportation. Entanglement, a cosmic dance between particles, reveals an intricate network of interconnections. One might even say that at the heart of the universe, everything is subtly dancing together, entwined in a cosmic jig of quantum mechanics. This is the extraordinary reality that quantum physics invites us to explore. The iconic double-slit experiment challenges minds. Imagine firing particles, one at a time, at a barrier with two slits. If these particles were like tiny bullets, we'd expect them to pass through one slit or the other, forming two bands on the screen behind. But that's not what happens. Instead, we observe an interference pattern. As if the particles are acting like waves, they seem to pass through both slits simultaneously, interfering with themselves and creating multiple bands on the screen. This puzzling result suggests that particles possess a dual nature, behaving both as localized particles and as spread-out waves. But things get even weirder when we try to observe which slit the particle passes through. The moment we measure, the interference pattern vanishes. Now the particles act like bullets again, passing through one slit or the other, not both. It's as if they know they're being watched. This is known as the observer's effect, a phenomenon that has perplexed scientists for decades. So what's going on here? This experiment illustrates a fundamental aspect of quantum mechanics, the principle of superposition. According to this principle, a quantum particle can exist in multiple states at once, until it's observed or measured. At that point, it collapses into a single state. The double-slit experiment paints a picture of a universe far stranger than we could have imagined. It tells us that at the quantum level, reality is not fixed, but exists in a haze of probability. It highlights the role of the observer in shaping that reality, and it demonstrates the inherent uncertainty and unpredictability of the quantum world. The act of observation or measurement alters the outcome, highlighting the observer's crucial role. The role of the observer and the question of measurement dive into the depths of uncertainty. In the vast expanse of the quantum world, the observer is not merely a spectator, but an active participant. The observer's role is not just to record what transpires, but their very presence can influence the unfolding of events. Consider a quantum particle in a superposition of states, a peculiar situation where it can exist in multiple states at once. Yet when we observe this particle, we find it in a definite state. This transition from superposition to a single state is what we call the collapse of the wave function. But here's the catch: the act of observation itself is what triggers this collapse. In other words, by measuring a particle in superposition, we force it to choose a state. It's as if the particle knows it's being watched. This concept is so counterintuitive that it has sparked countless debates among physicists, philosophers, and even theologians. Now let's take a step further into the realm of entanglement. Imagine two entangled particles. No matter how far apart they are, the measurement of one instantly influences the state of the other. This instantaneous connection, defying the speed of light, is what Einstein famously referred to as spooky action at a distance. Once again, the observer plays a central role. The act of measurement on one particle determines the outcome for its entangled partner. It's a dance of the quantum world, where the observer and the observed are intricately linked. The simple act of observation can influence quantum particle behavior, challenging our traditional understanding and raising profound questions about the unobserved quantum world. In the quantum realm, we are not mere bystanders but active players shaping the story. Is it then possible that our reality is not just out there but rather a co-creation with the quantum world? And if so, what does that mean for our understanding of the universe and our place within it? These are the questions that continue to intrigue us as we delve deeper into the quantum world. We conclude our fascinating journey into the quantum world, exploring superposition, entanglement, and the observer's role. We delved into the quantum universe, peeling back the layers of our physical reality to peer into the realm of the subatomic. We encountered electrons, protons, and neutrons, the invisible architects of our universe, and saw how they dance in a dynamic ballet of existence, exhibiting both particle and wave-like behaviors. We've journeyed through the concept of superposition, where quantum particles can exist in multiple states simultaneously, challenging our standard notions of reality. We've also explored the intriguing phenomenon of entanglement, where particles, no matter how distant, can influence each other's states in an intricate cosmic dance. We've witnessed the enigma of the double-slit experiment, where particles can demonstrate both their particle and wave-like nature, creating an interference pattern that challenges our conventional understanding of the physical world. The act of observation in this experiment alters the outcome, revealing the observer's critical role in the quantum realm. We've delved into the role of the observer and the question of measurement, which dive into the depths of uncertainty. The simple act of observing can influence a quantum particle's behavior, pushing us to question the very fabric of our reality. Each of these concepts, from superposition and entanglement to the observer's role, challenges our understanding and invites us to question the fabric of reality. These quantum phenomena open up a world of possibilities, shedding light on the unobserved quantum world and inspiring us to keep exploring the mysteries that surround us. Quantum physics challenges understanding and invites us to question the fabric of reality. Thank you for joining us on this journey into the quantum realm. We encourage you to share your questions, theories, or experiences in the comments below. Don't forget to leave a like, share this video with the curious minds in your life, and subscribe for more fascinating discoveries. Until next time, continue your quest for knowledge.